which will relatively define your period of the signal. You can define the delay time if you want any delay. If you don't want any delay, just don't put any delay time, right? Damping coefficient, you know, if you want it to die, right? If this is not going to be an ongoing sinusoidal signal, you want it to die. Like in this case, the one that has been shown here is dying, right? As you can see, it started, the peak was here, then the peak reduced, then the peak reduced, then the peak reduced, then later it will become just a straight line. Now, what has been happening here is damping. This actually is caused by resistors, if you put like resistors. So if you want a damping coefficient, if you want a phase delay, depending on you're having two signals, input signal and output signal, and you want to put a particular phase delay, depending on the components that you're using, inductor or capacitor, plus or minus 90 phase shift. So right now, I'm not going to go deeper into that. All I'm going to say, I'm just going to give no offset. No offset means my zero line is going to be in the middle. Offset means it means like a DC offset. What I'm saying is, if my peak-to-peak signal is 20 volts, my zero line is at 0, so it means 10 volts negative, 10 volts positive. If I offset it maybe by 2 volts, right? 1, 2, it means my peak will rise now from 10 here initially to 12 up here, right? But then my negative voltage won't go to minus 10 anymore. It will just come to minus 8, right? Because peak to peak has to stay 20. But if you put an offset, you're just offsetting it. If you put the offset, that offset to 10, let's say peak to peak was 20 volts. So 0 to negative peak was minus 10. If I put my offset at 10, it means my signal is no longer going to the negative. It's now going from 0 to 20 volts and back to 0 to 20 volts, back to 0 to 20 volts. That means I've offset the whole negative part of the signal. But in this case, I'm just going to run a simple sinusoidal signal. Offset is 0, right? Then my amplitude, I can define whatever I want. Let me just put it as 2 volts. In this case, amplitude 2 volts. Then frequency 1000 hertz, right? We don't want delay or anything. Just don't touch anything. I mean, we don't need anything. So 1000 it means my waveform will have a period of around 1 millisecond, which is not too bad, right? So just input this. The V is not necessary at this point. So just input this, then you just say okay, right? You say okay, then you leave that log, you go to okay, right? This properties box, do not do anything. You just say okay, right? Then you need to set this simulation now so that it knows you're now doing a transient analysis. So I'm just gonna go to actions again, simulation setup. I'm going to edit. Now I'm going to remove the DC sweep by transient, like what I said. Now on transient analysis, it will show me where do I want to start again and where do I want to finish, but in terms of time, right? Transient analysis, I told you, is time. It's analyzing the circuit between 0 to it reaches steady state. That's what it means. So I'm gonna just click here. Then it told me data time step. So it means at what time steps do I want to take this data? I want to take it at 1 second, 1 millisecond, 1 microsecond, 1 nanosecond. At what time step, right? So if I just write in this case 1 U, it understands 1 microsecond, right? 10 to the minus 6. Then total analysis time, like how much time do I want this analysis to go, right? 2 seconds, 1 second, 1 millisecond, whatever I want, right? 2 milliseconds in this case. All I have to know is that my time step and my total time analysis should be different, right? My time step should be smaller than the total analysis time. Then I can choose to start recording data at exactly the time I start the simulation. Then maximum time step, you can still choose 1 micro. Yeah, don't make it different to that. Then there's nothing complicated. Again, you just say okay, right? Once you finish that, you just say okay. It understands that's the transient gonna come in. I can remove that, it doesn't matter. Then you just say done, right? Now it understands we are going to run a transient analysis, right? You are going to run a transient analysis, right? Then on running, we do exactly the same thing, right? Choose this running guide, run simulation, run, right? It has finished its transient analysis. You say okay, then you go minimum. It will show us this is the output that is done, but we're not seeing much, right? We don't know what's happening here. So we want to see both voltages. We want to see what was the input voltage. Was it a true sinusoidal? What was the output voltage? Was it now a half rectified sinusoid? Let's see that. So what do? We can choose these actions or this action, same. So if you go to actions, then you go to scope, right? A scope comes up. So on this scope, we want to see what voltage and what voltage. So voltage at node number 1 and voltage at node number 2. Those are the two that we want to see. We want to see V1, which is our input voltage. Then we add that to our signal. Yeah, V1, a sinusoid, perfect. We define that. Then we want to see output voltage, which is voltage at node number 2, right? Or Y1. Look. Y1 and V2 will show the same because Y1 is the test point. Remember that test point that I told you to put, like you're just putting a cable, but you want to measure from that end, right? So V2 and Y1 will show you exactly the same thing. So I'll just go V2 and I'll add my V2, right? Now, let me just minimize this. Look. Now, I have my half wave rectified. Look, so when it was positive, I would get an output, right? When it goes to negative, at this point, my diode will not allow negative current to pass through. It will cut it off. Characteristics of a diode, right? It's a unidirectional component. It's unlike a resistor. A resistor, if I was to put a resistor there, then measure voltage across the resistor, it will just be exactly the same shape as the input signal, just a different magnitude. It will be V over R, my magnitude in that case. But in this case, look. Input voltage on, when it's positive, I have one output. When it's negative, it's 0. Positive output on the output. Then when it's negative input voltage, output is 0. Half wave rectification, right? Half wave rectification. That's what is happening right now. So I've seen that, yeah, I've got a perfect half wave rectifier, right? So then this was using a defined diode. That's already defined. But I can always choose to have my own diode, include my own diode parameters, blah, blah, blah. Then I will see the different characteristics of the output voltages, basically, of the diodes. But just to give a hint on what things you have to actually consider if you want to add your own diode, since I was just going to keep this one simple, so yeah, you can choose to save this or not if you want. I don't need it, right? So instead of this diode, now I just want us to just go overboard. Let's just remove this diode. Highlight it and just press delete, right? Now I want us to define our own diode, like what I was saying, just a few pointers. So just go to parts and just choose active diode. Just put this diode, right? This unknown diode, put it there. Then input. So if you go on the model type, you have to say to write an underscore, then it becomes a model, right? An underscore, then it becomes a model type. So the important parameters in a diode basically are their saturation voltage and the saturation current. And this N number, there's an N number in the diode, right? That's also important. So I'm just gonna add those parameters to just see what we can have. I just go on the model number. Let's choose this and enter our own parameters, right? Enter our own parameter. Let's just name it diode, whatever. Okay. Then what I told you is important is to add the saturation voltage, right? Saturation voltage, which is our IS, this one. This one. In this case, this is a predefined. Let me just put 2 times 10 to the minus 14. Then I'll just change this N value. Put it to 1.5. And say, okay. Yeah, I say okay. Right? If you want to see If you want to see what we just added right now, you can always click model, add. It will show on the model. Then you want to see these parameters in case you want to verify, you can add this, then you add the end that we just added and add it also. Okay, yep, it will show on the model parameters of the diode, right? Then what we'll do is just another operation point analysis, transient analysis, just to see what happens, right? What's the difference in the first experiment that we put and this experiment, right? So let me just do a simple operating point analysis. TikTok. Instead of transient, let me just do a simple operating point analysis, right? And let's just run this. Okay. Analysis complete. Look. 12, 11 volts. So it means the voltage drop across this diode is 0.9 volts. So if you define and give different sort of numbers, different what do you call them, different characteristics of the diode, then yeah, you're gonna have a different sort of output, right, on the diode. So on the operating point, let me just choose operating point and check all the boxes. Or let's do this. Okay, this is just to play around. Let's see what happens, right? What we can do, yeah, on this one. Now let me show you something. Action scope. So I want to choose V1, then I want to edit. I want to choose V2, I want to edit. It's still half-wave rectification, but if you're going to look at the first diagram that we have for half-wave rectifier and the second one, it's going to be different. This output voltage is different. And now, just to verify one thing, right? Let's see. And I'll add this. Look. This is Y1, the green one. Look. Y1 is green and V2 is blue. Why is that? As I told you, this Y is nothing but this test point. So it should give me exactly the same output voltage, right? So yes, this was just a summary of ICAP, like how you can use ICAP to do simple electronic circuit analysis, right? If you want to learn more about this, feel free to contact me. And again, thank you.